All right, lecture 6, couples and systems of forces. And what we're going to do today is I'm going to introduce the moment of a couple. Couples are really a concept I don't particularly like. I prefer to just think of things as forces, and a couple is just a pair of forces. But we'll kind of dive into it because there's a distinction. Well, it's not really. Anyway, you'll see as we go. And then we're going to talk about replacing a force with another force along a different line of action. But I mean, if you do that, you have to add in a couple or a moment in order to account for the fact that it's not on the same line of action. And then what we're going to do is we're going to reduce a system of forces to a force couple system, or what your book calls a wrench, which is a single force. So you've got a whole bunch of forces, and you're like, I want an equivalent system. Let's just get rid of all these forces and use a single force. Usually figuring out the force itself is simply a matter of adding all the forces and getting a resultant. But however, in order to make it equivalent, you have to think about where it should go. Okay, and so we'll talk about all that as we go into it. So I'm not going to, I'll probably look up a formal definition for a couple in a second. But here's all that a couple is. Okay, so let's suppose you go out to the car and you got a flat. I think your book even has a picture of this. Okay, so here's your flat, and you've got some lug nuts going around this thing, and you want to, well, usually there's 5, but whatever. And you want to take these guys off, right? So you take your wrench, and it's like this giant T-shaped thing, and you put it straight on this lug nut, and then and it's got like a bar coming out here. Well, usually it's not that incredibly long, but you get the idea. And you put your right hand on one side, and you put your left hand on the other, and depending on whether or not you're putting the lug nut on or off, you push down with all of your might. I don't know depends on how strong you are. Let's say you can put 50 pounds down here and 50 pounds here. Okay, so this is a couple. And what's important here, well, there's a few things that are important, but first of all, note that the resultant of these forces, so if I said the resultant of, I don't know what we want to call that, X and Y, or A and B or something. So if this is A and this is B, okay, we'll note that the resultant, if we add A to B, is 0. Okay, and I think that's pretty straightforward because one's up and one's down, so they have absolutely no effect on causing this lug nut. This lug nut does not want to go up or down. It kind of wants to stay where it is, but of course, it's got the threads on it, so that's forcing it in or out. But it's not going up. It's not going in the Y direction or the X direction, right? It's just trying to come, out towards us, so in the Z direction. Okay, so if Z is in or out, actually, I guess technically it wants to go in the negative Z direction. Anyway, so to kind of think about what these things are doing is that, the forces aren't causing it to go up or down or left or right because they are equal and opposite. However, there is a moment here, okay, that is being, so if I wanted to say, well, what is the sum of the moments on this thing from A and B? Okay, so I'm going to say around this point 0. Okay, what is that sum of moments? And so what I'm going to do is I'm going to add the moment from A, and I'm going to add the moment from B. Okay? In order to do this calculation, I'm going to need some distances. Okay? So this distance is going to be, I'm making this up as we go right now. We're going to say 1 foot there, and we're going to say 1 foot here. Okay? I'm just using a foot because it keeps things fairly easy. And so what we do here is we say, okay, well, the sum of the moments, about 0, equals, well, MA. So that's going to be, it'll be, can I write? Can't write. Okay. F times D perpendicular. And this will be to point A. This will be to point A, or to wherever A is acting. So I guess this will be point A. This will be point B. Okay. And we need to take care of a sign. And so in this case, let's see. This thing is causing it to, this force is making it want to spin in this direction. So that's counterclockwise, so that's negative. Okay? And then MB is making it want to spin in the same direction, so it'll be force at B times the perpendicular distance to B. Okay? And so we will go, okay, well, the sum of the moments, 0 equals, well, FA is negative 50 pounds, okay, times the distance to A, which is 1 foot, minus, well, here we go, 50 pounds is for the force of B, times the distance, the perpendicular distance to B, which is 1 foot. Okay, so the sum of the moments around 0 is negative 50 minus 50 equals negative 100 foot-pounds. Okay, foot-pounds. Okay? And that's how it works. Now you say, okay, well, that's cool and everything, but notice that these two were exactly the same. Okay, well, that makes sense because it's a couple. So they're each equidistant from that center point. So it makes perfect sense that that would work out that way. So usually for a couple, we don't do this calculation. We do this one where we say, okay, well, the moment of a couple, okay, equals, or really, I guess, the magnitude of the moment of the couple, equals the force times the distance parallel. Whereas for a couple, this distance is the distance between the lines of action of the two forces in the couple. Okay, so that's pretty standard for how we do this. All right, and so one of the interesting things about couples is if, I go back to my, changing the tire example. So if I'm like here and here, and I'm pushing down here with 50 pounds, and I'm pushing up here with 50 pounds, okay, and this whole thing is 2 feet this way, okay, and so now you can see that calculating the moment of that particular couple is fairly straightforward. You just go, oh, look, it's 50 times 2 is 100 foot-pounds. Okay, but one of the cool things about this is we can also create equivalent couples, okay, without, that essentially has the exact same effect on the system. So, for example, if instead I moved in and I put a force here, and I put one here, okay, and these two forces were, I don't know, let's suppose those are 1 foot apart, okay? Well, if this one right here is 100 pounds, and this one right here is 100 pounds, okay, that is an equivalent couple. It has the exact same effect on the system, okay? It's gonna try to loosen that lug nut the exact same amount, okay? And you can also imagine, you can imagine more extreme versions of this. Like, let's suppose we went all the way out, and you had a really, really long, wrench. Okay. So and that distance of that total wrench was, it looks like the way I drew it, maybe it's 6 feet. Okay. Well, then you would only need on these ends, okay, 16.67 or 667 pounds, I guess, going this way. And going this, well, I drew it all wrong, didn't I? Let's do it like this. Okay, let's delete a little bit. Okay, let's delete that. Okay. So basically 1/6 of 100. So 16.667 pounds and 16.667 pounds. Okay, and you can imagine just looking at that, you can go, oh, look, that's equivalent, because 16.667 times 6 feet is going to give me 100 foot-pounds. So it has the exact same torque. So this is why when you're working on that lug nut, you kind of know instinctively that you grab all the way out on the edges. You don't grab way down in by the center. Like if you were trying to create that same kind of torque right here, okay, it's just not going to work, right? You're going to have to be, you're going to be Arnold Schwarzenegger or something and put in, 1,000 pounds and 1,000 pounds because you've decided for some silly reason that you want to be 1/10 of a foot from the central nut, right? So that's just not going to work. Okay, so this is how it works, and this should be noted that this could be done in 3 dimensions as well. Your book has a great picture of this. Like let's imagine you had a box. Okay, and let's suppose it's a cube, right? If you apply 10 and 10 here, 10 newtons and 10 newtons. and this box is I don't know, 15 meters by 15 meters. Okay, the calculation of the strength of that couple is pretty straightforward. Like, okay, well, it's 10. It's the horizontal the perpendicular distance between these two lines of action. So it's like this. Okay, it's 15 meters. So you do 15 meters times 10 newtons, and the moment here is 150 Newton meters. Okay. Now, and this, I guess we'd have to think about the sign here. So in this case, this is counterclockwise, so it's positive, and that gives us our, that makes it a vector. Okay, but equivalently, we could have gone out to that box, okay, and had the equivalent system, if we have the exact same system, but instead you pushed, I don't know, let's suppose you pushed up here and down there. Okay, it's a 15-meter box. Oh, that should be a lowercase m. 15-meter box, right? And so this could be 10 newtons, and this could be 10 newtons, okay? And the moment there, oh, we don't want that. The moment there would again be a positive 150 newtons, okay? Because again, the perpendicular distance between these two forces is 15 meters, okay? And of course, you could think of any number of different varieties of equivalent couples. So I could bring my forces in close, or I could do something weird like, okay, let's suppose instead I wanted to push this way and this way on the box. Well, that certainly makes it more interesting, doesn't it? Well, in that case, I guess, the perpendicular distance between these two lines is kind of like across there, right? So that distance, for a box with a 15-meter sides, that distance would be 15 root 2 meters, right? And so this would need to be 10 root 2 newtons over 2, so 5 root 2 newtons. Okay, so this would be 5 root 2 newtons, and this would be 5 root 2 newtons. Okay, and in this case, we could do the moment here, and we'd say, okay, well, we got 5 root 2 newtons. Oh, root 2 newtons times the perpendicular distance, which is 15 root 2 meters. Okay, and the moment would be, 150, positive 150, because again, it would be causing things to go counterclockwise, newtons times meter. Okay, so that's the idea of a couple. And to me, I just tend to think of it as two different forces because calculating moments is pretty straightforward. And there's a nice trick, too, where you can say, well, I don't want to take my moment around the middle. I want to take my moment here. If you take the moment there, then you've only got one force to deal with because the perpendicular distance of this force is 0. And the perpendicular distance of this force is 15. So it becomes 10 times 15, right? So same idea. Anyway, so that's a couple, okay? And to me, it's a fancy word. It just means a pair of forces with opposite signs, but along the same, exact opposite direction, same magnitude, okay? And so it creates a moment. All right, so what we're going to do now is we're going to start talking about replacing one force with another force along a different line of action plus a coupler moment. Okay, so that's a lot of words. So I'm going to go over here and I'm just going to bring up a problem from your book and we'll work it. So, all right, so this is kind of a beautiful problem I've kind of stolen from your book. It's sample problem 3.7. And what we have is some kind of lever, here, and it's attached to, I don't know, it calls it a shaft. I don't particularly like, I don't know, to me, I guess sort of into the board direction, but whatever. Okay, so for whatever reason, around this point O, we have this moment, this couple, and this couple is formed by these two 200 Newton forces, one to the right, one to the left. Okay, and somewhere, a point 30 centimeters up the lever, there is a 400 Newton force that is applied directly downwards. And so what I want to do here is, I'm going to read to you what they asked for, and we'll talk about that a little bit. But really, I want to play with this problem, okay? Because I just want to give you an idea what it is that we're doing here. So what they want us to do is replace the couple and force shown, so what we have here, and they want to replace it so that basically it looks like this. Something like, okay, well, here's this, and here's our lever going off this way. Sorry, the iPad slipped in my hand there. So here's the lever. And what we're going to do is we want to just have a single force somewhere along here, okay, going probably straight down. Seems like that's highly likely. And that thing needs to be equivalent. Okay, I don't want to use the words, well, maybe we'll use like that to say it's equivalent. Okay, and so the question is, how much is this force and where does it act? Okay, so what is this distance right here? Okay, so that is not easy, right? So how do we do this? Okay, and so what I want to do is we're going to start with this moment. Okay, and we're going to not this moment, this couple. We're going to start by, I want to look at this point 0, okay, or O, I guess. Okay, and so we'll focus on that first. Okay, so I'm going to redraw this thing again, and, I can't really draw it that well. I wish they had given me a picture of one without any forces on it, or yeah, that would have been much better. Okay, so now, and I'm just going to draw the lever as like a straight line. Okay, so there you go. That's not a great drawing, but it's better than what I had up there. All right, so I'm going to focus first on this couple. Okay, so this couple right here, and it just looks like, well, let's see. So basically it looks like 60 newtons here and 60 newtons there. Okay, so, and obviously that's acting on the, on the, whatever we call that. They call it the shaft. I don't really particularly like that. Anyway, so like this, okay? And the radius of that circle is 60 millimeters. So the distance between these two is the diameter, which is 120 millimeters. Okay, so if I want the moment of that couple, okay, then that moment is going to be 60 newtons times the well, let's do it all. So moment equals the force times the perpendicular distance between those two. Okay, I don't even, I always put that little perpendicular thing in there to kind of remind me. Okay, so it's the forces times the distance between them. Okay, so in this case, or I guess really this is the magnitude here, is what's going to kind of work here. So anyway, so it's 60 newtons times the perpendicular distance, which is 0.120 meters. Okay, now I have to think about the direction in this case. In this case, the direction is, let's see, that is like a clock. So that will make it negative. Okay, so the moment, okay, and now I'll remove the magnitude sign because I just took care of that, is 60 times 0.120. So that's, I believe, well, 7.2, is that right? No, 8.4, excuse me. It's really bad math by my part. 8.4 newtons times meter in the counterclockwise direction. Okay. Oh, okay, major typo. All right, so fixing that, for some reason I put in 60 newtons instead of 200 newtons. Anyway, so if you use 200 newtons, all the little green numbers should be 200. And we'll end up getting negative 24 newtons times meters. So I can rewrite this problem now if I wanted to. Okay, because note, the net force of that couple is 0. Like, it's not pushing it to the right, it's not pushing it to the left. Those two forces are equal and opposite. They're just not in line. And so I could just, instead of writing those two forces, I can just write a couple, not a couple, a moment like this of 24 newtons times meters. Cool, right? And I can take this 400 newtons and I can keep it up here. 400 newtons. Okay, and this is an equivalent system. Okay, so everything is the same. Okay, so these two are equivalent. Okay, you say, well, that's cool, Wagner. What else can we do? Exactly. What else can we do? Thank you. You're a great student. So anyway, so we can go down here. We can go down here, and I can say, all right, well, let's draw this thing again. Okay. And let's focus on this 400 Newton force. Okay. So again, we've got 24 going here because I'm not going to mess with that one right now. Newtons times meters. It's clockwise, so it had a negative sign, so it's going clockwise. And if we look at that 400 newtons all the way up here at the top, we notice that we've got two lengths on it. We've got this 300 millimeters and we've got this 150 millimeters. So if we go down here, okay, well, I don't want to write it here. We'll write it here because I'll work from here. So it's going from here to here is 300 millimeters. And from the center of the shaft to the force itself is 150 millimeters. Okay? So what I want to do with that is I want to say to myself, you know what? I can't, I want to move this force around. So what we learned in the past was that basically I could take this force if I wanted to, and I could grab it. Well, I can't grab just the force right now, but let's see. Let's imagine this is my force here, okay? I can grab it, like let's suppose it's right there, and I could shift it, I could shift it along its line of action, and the force and the system is equivalent, okay? It doesn't really have any problems with me doing that, okay? Even if I put it over here and it's not even on the, on the diagram anymore, I can move it anywhere I want up or down this thing, okay? Now, if I want to move it somewhere where it's not in that line of action, so I want to move it here, I want to move it here, I want to move it here, you are allowed to do that, okay? But it comes with a cost, okay? So when you move it, and of course you could also move it, you could put it out here if you wanted, okay? But the problem is you have to account for the fact that the moment that this thing creates, here versus here versus here versus here, is not the same, okay? So what I want to do is first I'm just going to play and I want to move it here, and then I want to account for that moment. Okay? So I'm going to move it from up here, I'm going to move it down there. And by doing that, okay, I've essentially, if I move it there, I mean, maybe you can imagine this, but I have removed its moment around that shaft. Okay? Because now it's going right through the middle of it. So it's kind of like pushing on the middle of a hinge. Like it doesn't, moving it there does not cause this lever to move or to want to spin at all. So I've essentially removed the moment by moving it down there. So if I move it down there, I have to account for the moment that I lost. Okay, so what we're going to do is I'm going to go over here to this drawing. So I'm going to take it from up here, wherever it was, and I'm going to move it down there, and I'm going to give it its value, so 400 newtons. Okay, so from a force standpoint, we're all right. This has the same resultant forces on it as the system above, but the torque is different. The moment is different. So how would we calculate the moment of that 400 newtons? Okay, so I'm going to calculate the moment of that 400 newtons. I'll call it the moment 400 around the point, what did this call? Oh, point O. Okay, about point O. Okay, and we'll start by doing the magnitude of it. Okay. And so to do that, I need the force of the 400, okay, times the perpendicular distance, okay? And so what I'm going to do is I'm going to say, okay, well, the moment 400 comma 0, okay, the magnitude of that equals the force of the 400, which of course is 400 newtons, okay, times the distance, the perpendicular distance, right? So we need to remember that that is an annoying thing, but we have to think about, this is the line of action of this force. So we want the perpendicular distance of that force. So there's two ways to get at that. One would be to kind of like say, okay, well, this is a perpendicular distance to that force, but not to the line of action of that force, just to the force. And so that means I have to kind of get a force here and one here, okay, which is technically right here. Let me do that in yellow. Okay, so we could create a force here, and we create a force here, okay, to kind of get at this that that 400 Newton. Okay, I don't really feel like doing that when I can just take the force and slide it along its line of action until it's right here. Okay, so now I've got 400 newtons right there, and now I know it's 150 millimeters to the line of action of that force, 400 newtons. Okay, so we will use that. Okay, so this will be 0.150 meters. Okay, now I have to think about the sign on that before I take the magnitude sign off of this thing. 400 at 0.0. And what we're going to do is say 400 times 0.150, and that should be 60, I believe. 60 newtons times meters. And that is going to cause this thing to spin, looks like it's going to go counterclockwise, or excuse me, clockwise. So that's going to be negative, like that. Okay? So in other words, if I want to move this 400 Newton force from up here to down here, I can, but I have to account for the fact that, oh, look, there's an additional 60 newtons meters. Okay? So now this is an equivalent system. Okay? Now we say, okay, well, that's cool, but I don't really want to have two moments, which I think is fair. Who would want two moments? So we've got, a moment. So we've got this thing right here. I got this thing going off that way. And let's put our forces back on it. I really hate this red color. I'm sorry that I picked it. Okay, 400 newtons. And now we've got 84 newtons times meters here. Okay, that is equivalent. Okay, I think we're kind of getting, let's see, replace the couple and force shown with an equivalent, that should be equivalent single force applied to the lever. So we're not really there yet. Okay, but this is an equivalent system, right? Because we've replaced what we had to begin with, which was three forces. One, or really a force and a couple, but really 1, 2, 3. Okay, with a force and a single couple. Okay? Now that's cool. But what I want to do at this point is I want another equivalent system, and this is kind of what the problem is asking. Is it saying, well, I want a system that just looks like this. Okay, with a single force. And it seems obvious, or it should be obvious, that the resultant force is just going to be a negative 400 meters like this. Okay, or excuse me, 400 newtons like that. But the question is, where does it act? Okay, because it has to replace everything, including this 84 newtons times meters. Okay? So there's a few different ways to do it. What is most obvious to me, based on the way that we did the last one, is to say, okay, I'm going to move this force back up the shaft, or up the lever, excuse me. It's going to go this way, back up there. So what's going to have to happen is, basically, as I move it, that's creating a new torque. Okay, so it's kind of like, it's eliminating, so it's going to account for some of this moment that we already have here. Okay. So how far does it have to go up that in order to create 84 newtons times meters? So essentially the moment about that point 0 from that 400 Newton force needs to, it's almost like by moving it back up there, it's going to like suck this 84 Newton meter back into it, right? So this force here needs to account for this moment, okay? And if I move it too far this way, it's going to have too much moment. And if I don't move it far enough, okay, it's not gonna have 84 Newton meters. It's gonna have too little. Okay, so luckily, we know math here, so we know that the moment about point 0 needs to be, or at least the magnitude of it, needs to be the force times the perpendicular distance. Okay, right? So I'm going to do the perpendicular distance. There's a lot of different ways that you could do this. So what I'll do is I'll say, okay, well, the moment 0 equals, we know that moment, don't we? There's no reason to write that. We know what the moment this thing has to have. It's 84 newtons times meters. Okay, equals the force, which is 400 newtons times meters. Okay, times that perpendicular distance. Okay, and well, this was a negative. Okay, and of course this is generating a negative moment, so that's fine over there. So then we'll just do a little math, and the perpendicular distance becomes equals 210 millimeters. Okay, noting, of course, that this thing right here, from here to here, is what is that number, 210 millimeters, or 0.20 meters. Okay. Now that's all fine and dandy, but the question didn't ask for that. It actually wants to know what the distance is, that I wrote in red here, or I'll highlight in green. It wants to know this distance. Okay, so now we just have to break out our trig. Okay, so if I go up to the shaft, now there's a few different ways to do this trig. You can use the fact that this angle is 60 degrees. Okay, and I'll do that too. But I would just take note of the fact that this distance is half of this distance. Okay, boom, done. Okay, which means if this one is 210, this one is 0.420 meters. Okay, and that'll solve it. If you want to use the trig, because a lot of you are more comfortable with that, we can say, okay, we're dealing with a cosine because that's an adjacent angle. So we can say the cosine of 60 equals the adjacent 0.210 divided by the hypotenuse. Okay, and you can solve that. But the thing is, the cosine of 60 by definition is a half. Okay, which we know because, like, look up here. Okay, the adjacent and the hypotenuse, the ratio is 1/2. Okay, so yeah, so if you plug this in, you'll get the hypotenuse equals 0.420 meters. Okay, so in the end, what this all tells me is that this thing right here, well, actually, I think I started to draw it way up here, didn't I? Yeah, so we can go up to this thing right here. Okay, and I can say, well, look, if I take this original drawing and I just put a 400 Newton force right here, and I put that thing, that was a really bad drawing I did earlier, wasn't it? And I put that thing 410 millimeters this way. Okay, that is equivalent to this. Okay. And of course, it makes some sense in a way. I mean, if you think about this original system, okay, like if I can delete some of these, all these crazy markings I have on here, so it can be a little bit clearer. But if you think about this original system, you're like, all right, I want a single force. Well, obviously, this is the only force that, this vertical force is the only force that really has any effect as a force, right? These other two just have effect as a couple. Well, I need to get, if I want to absorb the moment of this couple into that force, I need to move the force further this way. Okay, so basically I'm saying, I'm starting with this, and I'm adding on, a moment down here. And what I want to do is I want to absorb that moment into that force in such a way that everything's accounted for. Okay, and that's what this did. That's what we just did. Okay, we did it. Okay, that was the goal. Okay, and well, I have a whole bunch of drawings of that. Crazy drawings in the book. Oh, look, they did the same drawings I did. That's cool. I didn't really look at them that closely. Anyway, let's move on to something else. All right, so let's scroll on over. Let's see what we got here. This is another example from your book. I'm doing these because I really like the drawings and whatnot. So we're going to do the next two. Okay, so here we've got some sort of, I don't know, beam or something, and it's got four forces on it: 150 newtons, 600 newtons, 100 newtons, 250 newtons. Some are up, some are down. And we want to reduce this system of forces to A, an equivalent force couple system at A, B, an equivalent force couple system at B, or C, a single force resultant that is equivalent. Okay, so that is the so-called wrench. I've never heard it called that, but I really liked it. So I should have just called this lesson the wrench. Anyway, so we're going to reduce this thing. And essentially, for A, what we want this thing to look like is we want it to look like this. Let's see, I'm going to zoom over here and kind of show you what it's going to look like, more or less. Okay. Yeah, so maybe like beam, and then there's a roller right here, and these things are like this. So at A, we're going to have an equivalent force. I don't know if it's up or down, but it's going to look something like that, and it's going to have a moment. Okay, and that moment, again, I don't know if it's going to be clockwise or counterclockwise. Okay, for B, same idea. Okay, but we're going to be at location B. Okay, again, and I don't know if it's going to be clockwise or counterclockwise. So it'll look like that. And then for the wrench, we want it to look like this. And it's going to be a single force somewhere along there. And again, I don't know if it's going to be up or down. Okay, so that's our goal here. All right, so I'm going to kind of bring this guy with me because I want to keep him. Okay, maybe we'll just copy him. This is a great world we live in. We can do whatever we want, right? So let's just have a little thing for us to look at from time to time, kind of keep us grounded here. All right, so the first thing I want to do so this is for part A. Okay, so for part A, what I'm going to want here is I need to know the resultant. Okay, and this guy, the force resultant, is going to apply to all of them. So maybe I'll do that right here because it'll be for all of them, right? So that's going to be for all these forces. They don't have names. I'm not going to, I could name them. I'm not going to bother naming them, okay? They're named the 150, the 600, the 100, and the 250, okay? So the resultant force here is 150 newtons in the J. We'll go ahead and use I's and J's here. Minus 600 newtons in the J. Plus 100 newtons in the J. Minus 250 newtons in the J. Okay? And so that's pretty straightforward, right? Our resultant force, in this case, there aren't even any angles here, right? Is negative 600 newtons in the J. Okay? Now, of course, we're making an assumption here that this is X and this is Y and that Z is coming this way, okay? Which is, of course, pretty hard to see because I didn't draw this very well now, did I? So anyway, all right, so that's it. So now we've got this resultant, and it's almost certainly going to be the thing that we have for the rest of this problem. All right, so now what I want to do is I'm going to take each one of these forces, and maybe what I'll do is I'll kind of draw them. They are in red. So, just draw them, and I'll simulate what happens as we move them, okay? So each one of these can be moved separately. So I'll kind of take this guy, and I'll put him right over that 600, and I'll take this one and put it right over that 100. Take this one and put it over the 250, right? And so now we've got, let's see, here's our beam, something, well, let's do it in a different color. Let's do it in white, because to me, white shows up the best. Okay, like that. And we're focusing on this point A. Okay? So I want to know the moment at A. Okay, so I'm going to use the, what I'm going to note here, the moment at A, the resultant moment at A. This is your book's notation. I have avoided using it. Okay, so this is going to be the sum of the moments. So I'm going to use the sum of force times distance. Okay, force times distance, like that. Okay, each one of these forces, when I move it over, I have to account for its, the effect of its force, right? So I forgot one of these. I forgot this one. Oh, no, don't do that. Let's erase it. And, all right, let's draw it down here so it won't grab something else to go with it. Okay, so we're going to grab this one, and we're going to put it right there. All right, so what we're going to do is just going to go force by force, and as we move them over, we're going to account for their moments as we move them over. Okay, So we're going to start here with sum of the moments AR. Okay, boom, equals. Okay, so the sum of these. So the first force. Well, I don't have to move that thing at all. And its perpendicular distance, so if I move it from here to nowhere, so it's just staying here, well, it has no effect at all. Okay, so the first one is just a big fat 0. Okay, 0. It didn't get moved. Okay, so it's fine. All right, so then we're going to take the second one, and I'm going to move it from here to here. Okay? As I move from here to here, right, then I have to take into account that the original force had a moment that was 600 newtons times 1.6 meters, so that's the perpendicular distance, right, back to A, and then causing it to spin this way. Oh, well, I lost it. It kind of got stuck back there. Come on, punk. Oh, that's unbelievable. All right, so anyway, so, you know, it's right here, and it's causing this thing to spin this way, which is clockwise. Okay, so I move it over here, so it's going to have a negative sign because it's clockwise, negative. The force is 600 newtons. Okay, and the distance is 1.6 meters. Okay, so then I'm going to go to the next one. Okay, this 100 newtons was happy here, but we moved him over here. So we're replacing this 100 newtons with 100 newtons plus whatever its moment was. Okay, and this was causing this thing to spin counterclockwise, so it's going to be a plus sign. Plus, and that's 100 newtons, okay, times that distance, which is 2.8 meters, like that, okay? And then we've got this last one, this 250 newtons, which again, I'm going to bring it over here, and as I bring it over there, I need to account for the fact that it wants this thing to spin clockwise some amount. So clockwise is negative. Okay, so 250 newtons times, well, that's 4.8 meters. Okay, and that's the number we're looking for. So the sum of the moments about A equals, okay, equals negative 1880 newtons times meters. Okay, where that negative sign indicates that we are going in the negative, so it's going to be counterclockwise. So, so our equivalent system here, now that we put all those forces on top of each other, we've got a resultant here of negative 600 newtons, and we've got a counterclockwise moment, like that, of 1880 Newton meters. Okay? So that's it. Okay? Now, I'll note for part B, okay, because it's the same problem again, okay, but we're moving it to the other side. So we want to note one thing here, which is that we can do exactly like we did a second ago, and I can sum up all 4 of the forces, just like I did for part A. Okay? I could just go back to the beginning and do that. Or what I can do is I can start from part A, and I can take this 600 Newton force right here, and let's see if I can grab it. I can't grab it, but, you know, whatever. I could grab one of these. Oh, I can't grab one of those. Let me grab one of those. No, I can't grab one of those. Okay. I could take the 600 Newton Newton force here, and I could just slide it along here over here. Okay. So now I still have this over here, 1880 newtons times meters, and I've got 600 newtons here, okay? But by sliding it, I have to take into account what its effect was on point B. Okay, so I can't move a force not along its line without taking into account whatever its effect was on the original, you know, what its effect was. So this one right here, the 600 Newton force, I think you could see if you think about it, it was causing this thing to spin this way around point B, right? So we know there's going to be a moment right here. Okay, so the moment at point B from that, from the resultant at A, Let's see how your book uses that, labels that thing. They don't really give it a name. Oh, they call it the. Yeah, whatever. I'm gonna leave it like this for now. That's a really silly notation, but just trust me, and you'll understand why in a second. So that's going to be equal to the moment that this force was exerting onto B. Okay, so its perpendicular distance is the whole length, so it's going to be 600 newtons. Okay, this particular moment is counterclockwise, so it's positive. Okay, and the perpendicular length is, let's see, 1.6 plus 1.2 plus 2, that's 4.8 meters. Okay, so the moment of B, comma RA equals, okay, 2880 positive newtons times meters. Okay, so that's cool. But now I've got this drawing here, 2880 newtons times meters. Okay, but it's not really what I wanted, right? I wanted a nice pretty system like I had at A, where there's only a force and a moment. Okay, so let's go here. Let's redraw it. Okay, I still have this 600 newtons going down. Here's my point B. And what, are these moments hurting each other or helping each other? Okay, I think if you, well, there's an error here. Did you catch it? Did you catch it? Okay, I can see it now, but I missed it earlier. Okay, so anyway, everything I said is correct in the idea, but the thing I messed up here is this guy right here. Notice this means clockwise. Okay, which way did I draw it? I drew it counterclockwise. Okay, so let's do this. Let's erase this, the head of this arrow. If it will erase, there you go. Let's make it go that way. Okay, if it will do that for me. And then we'll go down here and we'll fix this one as well. Okay, and if it will erase, I have a feeling that it will erase eventually. Maybe after I fall asleep or something. Okay, so we'll go, come on. We'll go back down here, and I'll ask that question again. Are these two helping or hurting each other? Well, they're turning in, these two moments are going in the opposite direction. So they're going to cancel each other out, okay, to some extent, okay? And I think if you can see, it looks like it's going to be 1,000 in this direction, okay? 1,000 newtons times meters in the counterclockwise direction. Okay, so the way you would solve that is you would say the sum of the moments about force B resultant equals this, what do we call that? 1880 newtons times meters. Okay, and that was negative, plus the 2880 newtons times meters. Okay, where we keep these signs. So this one right here goes right there, and this sign goes right there. And the signs take care of it for us, okay? And that's like a wonderful thing that will happen if you do this correctly, okay? So there you go. Got them. All right. So the last one I'm going to do is a little bit more difficult. So we're actually going to use the I's and J's, and we're going to be a little bit more formal with it. And it's a bunch of tugboats. So, oh wait, I forgot part C, didn't I? Okay. So before we go to these tugboats, let's look at part C, the quote unquote wrench. And what we're going to do is we want to replace it with a single force, such that I can kind of get rid. So we notice that if we look at A to B, so A and B both have the same resultant force. Okay, so if I circle it, they both have the same resultant force. But this one has a moment of 1880 going clockwise. This one has a moment of 1,000 newton meters going counterclockwise. So somewhere in between there's the point where I could just apply this 600 and have no moment at all. Okay, so I'm going to redraw system B, or you know what? I'm not going to do that. I'm just going to erase some of what I just did. And no, that's fine. All right, so what we're going to do here is we're going to move that 600 force. Okay, so I'm going to take this thing like this. So I'm going to imagine that it starts here, and there's going to be a new point somewhere along here. We'll call it 0.0 or something along those lines, right here, let's say. And what I'm going to do is I'm going to move this force along here until it's at O, or I'm going to move O, really, until by moving it over here, what's happening is, I still have this 1,000 newtons. It's still staying where it is, but the 600 is moving to the left. And as it moves to the left, I have to take into account the fact that what effect it is having around 0.0. Okay, so if we think about it, where it is now relative to 0.0 is going to create a, what is that? That's clockwise rotation. Okay, so so what I want, though, is I'm going to want that clockwise rotation like this. Wait, clockwise rotation. This is very tricky stuff. So what we want is that clockwise rotation to exactly counter the moment that we already have, right? So we essentially want that clockwise rotation to be equal and opposite to this 1,000 Newton meters that we already have. So how do we do that? Well, we know this is our distance, our perpendicular distance. Okay, and so I can say right off the bat, if I wanted to be formal about this, I would say the sum of the moments about O need to be equal to 0. Okay, and so I would say, well, we've got, so that means that we've got 1,000 Newton meters. Okay, and that is counterclockwise, so that's positive. Okay, minus 600 newtons meters. Okay, times whatever that distance, whatever that is. Okay, and I can solve for that using this equation, and it's what, 10 divided, or 1,000 divided by 600, so that's 5/3, so 1.67 meters. Okay, and if I wanted to know, let's say, distance from A to 0 would be 4.8 minus 1.67 meters. Okay, because this is the whole beam, and this is just the portion on the edge. So distance from A to 0 would be, well, what is that? 1.13 meters. Okay, excuse me, 3.13 meters. Okay. Okay, so that would mean that the equivalent system, the answer for part C would look like this. We would have a force down here, and it would be 600 newtons, and it would be 3.3 meters from this side, 13 meters from this side, and from this side it would be 1.67 meters. Okay, and that would be the answer to part C. Okay. Sorry, that got a little sloppy at the end there. I grew up really loving tugboats, and so I kind of want to get to the tugboat problem. So let's go find the tugboat problem. Oh, here it is. All right, here we go. So all of these problems are the same. Okay, we just keep doing them again and again and again. Okay, each tug, there are, looks like 1, 2, 3, 4 tugboats, and they're pushing on this bigger boat. And each tug is pushing with 5,000 pounds of force. Okay, so what they want us to do is they want us to determine the equivalent force couple for a system, or it's the equivalent force couple system at O. Okay, so I don't know how visible O is yet. Okay, O is this red dot right here. Okay, and determine a single point where a single tug, so this tug is going to be pretty kind of like a beastly tug, could push and have the exact same effect. Okay. So tugboats are like really cool. I grew up loving tugboats, because I'm a crazy person and everything. But anyway, so let's zoom in. Or you know what, we're going to do the whole duplicate thing because I want to be able to keep this around wherever I am. So we're going to duplicate it, and I'm going to zoom in. And what we're going to do is we're going to very quickly, I'm not going to spend a lot of time on this, you have to be able to do the trig here, is we're going to define these forces, okay? And again, we're going to be a little bit more formal with this one. So we'll do X and we'll do Y. Okay, so let's kind of walk through this fairly quickly. Okay, so this is 5K in the negative J direction. Okay, this one right here, let's see, force number 2 here, this is a 3, 4, 5 triangle. So if this is 5K on the diagonal, this is going to be 3K. Let's zoom all the way in. Okay, in the I direction. And this will be 4K in the negative J direction. Okay, so right now in the J direction, the negatives are winning. Okay, let's see this one over here. Okay, we've got 5,000 on the diagonal. Okay, but we've got an angle of 60 degrees, which is right here. They kind of drew it way out there, right? So this one is 5K. Okay, this one is going to be 5K times sine of 60. Okay, 4.3301K. And this one right here will be 5K cosine of 60, which is going to be 2.5K. Okay, and then we'll go over to this 4. And that, of course, is the easiest one because it is both, because they'll both be the same. And so it'll be 4 times either the sine or the cosine in this case because they're both the same. Or it's 4 root 2 over 2. So it's, 2 root 2, which 2 root 2 equals 2.82, 2.8284K, and 2.848284K. Too many sig figs. It's such a pain in the butt. All right. Oh wait, no, that's not right. Let's fix that. This is 5 times the cosine of 45 and 5 times the sine of 45. Okay, so this is their 5K, and this becomes 3.5355, and this is 3.5355K. Okay, so that's an awful lot of kind of, just trig. Okay, so we want to kind of turn this into a, the appropriate relations for the resultant force. Because what we're trying to do is we're trying to basically move all of these to this red dot over here, okay? And it's now a Santa Claus dot. And so the first thing I want to do is I want to get the resultant, okay? And so what I'm going to do is I'm going to add all these suckers up, okay? So we'll go in order. Force 1 is, let's see here, negative 4.3301K in the J. I usually do I's first, but I guess it doesn't matter because the I's and the J's take care of you, right? It keeps you from screwing up, okay? I. Okay, next one, minus 4K in the J, that's number 2, and then plus 3K in the I. Okay, force 3, minus 5K in the J, and then the last one down here is we're going to have plus 3.5335 kips. So, oh, by the way, kips is a kilopound. Okay, so we're in the J plus 3.5335 kips in the I. Okay, so if I add all those up, we're going to get the resultant, and right here I will make sure to get the I's first. Okay, so it comes out, to be some numbers, okay? And what we're going to want out of those two ultimately is we're going to want to kind of turn them into a force with an angle. So I'm going to go ahead and do that right now. So we'll use the Pythagorean theorem basically. So, this is 9.0335 in the I. Okay, and this is negative 9.7966 in the J. And so I want to know this side and I want to know this angle. Okay, so we'll go ahead and do that. That side is the square root of the x component plus the square root, plus, you know what it is. Okay, so this side right here is the resultant, the magnitude of the resultant equals the square root of, you know what, I'm going to pause it and just write it all down. Okay, so if we just kind of do the math on that one, so basically trying to figure out what this angle is, theta, and what the magnitude of the resultant force is. This is kind of what you get. Okay, so If you need to spend some time, pause it and make sure that makes sense to you. Okay, so, all right, so going back to the main problem. All right, so here we go. We've got these two resultants. We know the resultant in the x direction, and we know the resultant in the y direction. Okay, so what we're going to do now is we're going to start, I want to start moving these forces to the location 0. And this is more complicated than what we've done in the past because we've got two directions, and we've got some angles too. So, but the nice thing is we don't have to deal with the angles because I've converted everything into x and y coordinates. It just means we have more forces because we've got x forces and y forces, but we don't have any thetas to worry about or any alphas or betas or anything like that. So, so let's go ahead and do it. Let's move each of these to the point, to the point O, or the red dot right here, okay? So we're going to start, and we're just going to go one at a time, okay? So I'm going to try to use the notation your book uses. So we're going to say the sum of the moments around point 0, the sum of the resultant, okay? So that's all of the forces, or all the moments from all the forces and any moments or couples that might be generated, okay? Okay, so this is going to end up being a very long line because there's a lot of forces here, okay? And let's just take them one at a time. So I'm going to map them from above. So like I'll just kind of mark them off as we go. Okay, so we're going to start with this 4.3301 kip force. Okay, so let's zoom up there and let's look at it. Okay, so this whoa, I didn't want to do that. Okay, so this 4.3301 kip force. Okay, it's right. I've drawn it right here, but it's actually acting right here. Okay, so what is its distance? It's perpendicular, so I can move it along its line of action. So this is its line of action right here. Okay, because it's a vertical force. And its perpendicular distance is 90 feet. Okay, so I will multiply that by 90 feet. Okay, and then we have to think about, is this thing around, by moving that force over to O, so now we've got that force that's kind of acting like right here. Okay, what moment did I remove by bringing it over there? Okay, so initially it was causing this thing to go, okay, and this is going to be white, so it'll be a little bit hard to see, but like that, right? So that's counterclockwise. Okay, so that one's going to get a positive sign. Positive. Okay, next force up, 2.5 I. Okay, so here's the 2.5 in the, will you please zoom in? Okay, in the I direction, so that's this one right, this is really obnoxious. That's this one right here. Okay, and notice it's acting at the exact same point. So it's acting this way. And its distance is 50 feet. Okay, its perpendicular distance is 50 feet. Okay, so we can go back over here. This is really obnoxious. Okay. Oh, and what direction is that? Well, let's see. Looks like it's going to be going this way. So that will be clockwise. So it'll have a negative sign. That'll be 2.5 K times 50 feet. Okay? Now we want to deal with this 4J. Okay, so let's go up here. Okay, the 4J, note, is happening right here. Okay, and it's a force going down. And it is going to be, its perpendicular distance is from here to here, so that's 100 feet. So it's going to be 4K times 100 feet, and it is creating a, is that clockwise? Clockwise rotation, so that's going to be negative. Okay, so we'll go over here, and we'll have negative 4K times 100 feet. Okay, now hopefully, you know, the more of these we do, you'll start to see the pattern here. Okay, so the 3K. Okay, well, let's use a different color here. Here's our 3K right here. But of course, it's acting at this point right here. Okay, so its distance here is, well, we can see it on the back of the boat, is 70 feet. Okay, but its net effect going this way is going to be to cause this thing to spin, that looks like clockwise. So we're going to go with a negative 3K times 70 feet. Okay, so now we've got a 5K in the back of the boat somewhere. Let's go back to red maybe. Here's our 5K. Okay, now what's its acting right here. So its distance is from here to here. Okay, so that's, let's see, 100 plus 200 plus 100 is 400 feet. So we've got 400, and it's causing things to want to spin this way. Okay, if I could draw the whole thing. So that's clockwise, so that one's negative as well. So what do we say, negative 5K times 400? Negative 5K times 400 feet. Okay. Now we've got these two 3.55, 3.5335s, whatever. Let's do this first one, the one in the J direction. So again, it's acting here. Okay. And it's acting in this direction. So its perpendicular distance is right here, is 300 feet. So we'll go down here, and we'll say 3.5335K times 300 feet. And I didn't remember which sign that was. Okay, so if we look at it, it's going up right here, so it's causing, that is counterclockwise rotation. So that's a plus. Okay, and then the last one, I mean, this is getting really, really sloppy. Hopefully you're, able to manage your sheet of paper better than this. I mean, normally when I do this, I don't draw these circles, but, hopefully it's helping. Okay, so then that one is acting right here. Okay, the 3.5355 is acting in the J direction, so it's going this way. So its perpendicular distance, if we were to do this, is from here to here. Okay, so that's 70 feet. We're assuming the boat is symmetric, like this, right? So that's 70 feet. Okay, so it's going to be 70, and its net effect is going to be to go this way, which appears to me to be counterclockwise. So that'll be a plus, okay, plus 3.5335K times 70 feet. Okay. Woo. Doozy. Okay, let's see if I can zoom. Hopefully you read them all as they were created, because I'm just going to punch these suckers in a calculator and get a number. All right, so if we zoom in here so that we can just kind of clean this all up, we'll say the sum of the moments, I wish we were in white, but I accidentally am still in blue, was negative 1037.9. And that is, the units for that is kips, so kilo-pounds, feet. Okay, so, I don't remember. I guess we'll say pound kips. Okay, foot-pounds. So maybe pounds, no, that's not right. So it needs to be foot kips. I don't know if they make that. Anyway, that's certainly a unit. I'm going to leave it like that. Okay, so it's a length times a force. Okay, so kip is a kilopound, so it's 1,000 pounds. Normally you would have this as foot pounds. So then you would have to multiply this by 1,000, and so it would be a rather large number. So we'll just leave it like this for now. Okay, so now we've got this is our moment at O. Here's our force at O. Okay, so I can draw determine the equivalent force coupled system at O. Okay, so we can go to O. I can draw a boat, however I want. It looks like 4th of July on this paper right now. Here's my boat. That's my boat. Sorry, you guys didn't watch Forrest Gump. You should probably go watch it. Okay, and so we've got a force going like this, okay, at an angle of 47.3 degrees, 47.3 degrees, okay, and this is 13.3 kips. And we've got a moment around it, which is negative, so it's going counterclockwise around that point of 1037.9 foot kips. Okay? And that's the answer to part A. Okay, kind of a lot of work. Let's do part B. We're running out of time here. B, we want one huge tug. All right, so for part B, this is a little bit complicated, okay? And what we want to do is we want to move this force right now, which is acting at point O, and we'll move it somewhere where a tugboat can push this boat in a way that works. Okay, so the problem with this one compared to our past problems is that it's in 2D and well, it's in 2D, okay? So the first thing I want to note is that the tugboat is, we know the direction the tug is pushing, okay? It's pushing down and to the right. So it's going to have to be this giant tug, whatever it is, it's going to be pushing with 13.3 kips, okay? And it's going to be pushing somewhere up here, okay? Because it's going to be on the side of the boat, right? It's not going to be, it doesn't pull. This is a tug. Well, tugs do sound like they pull. Let's imagine that like all the other tugs in this problem, it's pushing. Okay, maybe the book does it a different way, I don't know. But it's definitely up there somewhere. You know, I would make it a push because all the other tugs are pushing. Okay, and it's pushing with 13.3. But I'm going to go back, I'm going to break that thing back up like this into the forces that we had in the beginning. Okay, we had an X force and a Y force to give us that 13.3. So if I go back up there, let's see, we had 9.033 5 in the X, okay, that's a little K, and we had 9.7966 K in the J. Okay, so that is what's acting on the edge of this thing, and I still have a moment right over here somewhere, O, okay, and that moment has a magnitude of 1037.9 K. Okay, so I'm moving my force, and so now I'm going to center everything around this point right here. So the force was over here at O, but now it's up here at, I don't know, I'm going to call it T for the tug. Okay, so what was the effect of that force? Well, let's see. The downward force was causing a counterclockwise rotation. So I can say the sum of the moments about point T resultant, I'm going to want that to be equal to 0, right? So I've got one force already accounted for, the 1037.9 kips, okay? The effect of leaving the 9.7966 kips over there would have been, right, so by moving this force to T, I'm eliminating the torque that it, or the moment that it had about T. So when I move that force from here to there, okay, I'm eliminating the fact that it wanted to turn things that way. Okay, so unfortunately I don't know how far in this direction I moved it, right? But I do know that to calculate that moment would have been, so it's going to be, let's see, we said, so that's counterclockwise, so it'll be plus the force, 9.7966 kips, times that distance, which I don't know what it is, so I'll just call it x, because that's easy enough. Okay? Now the other force, okay, the horizontal force, was here, and now it gets moved up there. Okay, and its effect was, it turns out, also counterclockwise. So plus, okay, 9.0335 K. But we know how far it had to go. It had to go this far, which according to our diagram earlier was 70 meters, I believe. Yeah, or 70 feet, excuse me, 70 feet. Let's keep track of our units here, what systems we're on. So, come on, you can erase. Thank you. 70 feet. So we know that this is going to be 70 feet. Okay, so I can solve this equation right here for x. Okay, x, and that will tell me really, well, how far down the boat from O we want this thing to be. So there it is. X equals 41.4 feet. Okay, so busy stuff, lots of stuff. We'll probably have a test on all of this stuff 2 weeks from today. And next week I'll kind of just work a bunch of problems. I don't know if I'm going to introduce anything new, but my plan right now is to introduce a bunch of problems, okay? So hopefully, while kind of delving through this stuff, you kind of got an idea of what we're doing here, okay? The couples and the systems of forces. You know, the single tug is the quote-unquote wrench. And hopefully the moments are kind of coming clear. So anyway, take care of yourselves. I won't see you again, but you know, it's very sad for all of us. Hopefully you're taking care of yourself, and have a good day and a good night and all that other stuff. And be easy, and you know, take care of each other and help each other. And I'll talk to you later. Okay, bye. I didn't want to